Hello, today we're going to talk about structure 2.2.7, which is all about covalent network bonding. So certain types of atoms will form this expanded network of covalent bonds. That's why it's called covalent network. Some people call them giant covalent molecules. But effectively, you're going to have your atoms connected with covalent bonds to other atoms. But then it's going to continue with more covalent bonds. And then those can continue and form more covalent bonds. And so you wind up with this huge lattice structure, and there are different structures depending on the atom and the specific allotrope that you're looking at. But it's all covalent bonds. Whereas when you have individual covalent molecules, let's say carbon dioxide, they're not forming covalent bonds with any other atom. They can form intermolecular forces with other molecules of carbon dioxide, but it will not form any other covalent bonds to any other atom. Just these two double bonds. Covalent network, it can keep going depending on the number of atoms available and the specific allotrope that you're working with. So carbon is one of the atoms that forms these covalent network structures. And they can attach in different ways. Carbon is super versatile because it has 4 valence electrons, so it can form 4 covalent bonds. And there's a few different allotropes or structures of carbon that you should be aware of. So you have diamond, graphite, and graphene you should probably know. And then one that's just kind of fun is fullerene. I don't know that you'd actually be tested on that per se. Anyway, but definitely need to know diamond and graphite for sure. Diamond is where the carbons are in an sp3 hybridized formation, so that every carbon atom is attached to 4 other carbon atoms. Every carbon atom is attached to 4 other carbon atoms. And so it makes this very, very strong 3-dimensional lattice where all of the carbons are attached to other carbons. And so it makes it have this really hard structure. It's one of the hardest substances that we know of. It's also a really good thermal conductor. And it's very, it's transparent. And it's cannot be scratched by other materials. It can be scratched by diamond, but it can't be scratched by other materials. It also has a very, very high melting point. So that's for diamond. Graphite, on the other hand, is sp2 hybridized. Okay, so that's where you're seeing these trigonal planar structures where each carbon is attached to 3 other carbons. And because it's for 3 of them, it looks like this. And so you wind up with this flat sheet of carbon atoms. It's a little hard for me to draw. Let's see if you can imagine this is a sheet of just carbon atoms. And I'm going to tilt it on its side so it looks like a sheet of paper. A single sheet would be graphene. A single sheet of graphite would be graphene. But if you have multiple sheets, that's where you get into graphite. And these sheets are attracted to one another by intermolecular forces only. And so graphite is what some people call pencil lead. It's not actually lead, but it is the material in pencils that they use now. And when you're writing with a pencil, one of the sheets of graphite will come off as you're writing. And then if you continue writing, more sheets of graphite go onto the paper. So you have these sheets that are attracted to one another. Okay, it winds up being a really good electrical conductor. And it's because, carbon has 4 valence electrons, but right now they're forming just 3 covalent bonds. So by having that extra space effectively, it allows the electrons to move around the structure very easily. So graphite, graphene, really good electrical conductors. What's interesting about graphene is that because it's just one of those sheets, you can actually roll up the sheet into a tube and make a carbon nanotube. And you can make carbon nanofibers or carbon fiber, and you can even weave those fibers together and make these super strong structures. So carbon is super interesting. Another kind of neat one is fullerene, which again, I'm not sure you really need to know about, but effectively it makes a sphere of carbon atoms, right? Where the center of it is open or empty. And they've been doing some research into seeing whether like you can use fullerene as like a drug delivery system by putting stuff in the center. I don't know how far they've gotten with that kind of research, but it is really cool. Like you're effectively making like this soccer ball of carbon atoms on a very, very tiny scale. It's very, very strong. But yeah, just kind of neat. I wouldn't necessarily memorize it for the exam. Another atom that is important for covalent network bonding is silicon. And it's because silicon is also in the same group as carbon and it has 4 valence electrons. What's interesting is that silicon tends to form its covalent structure with oxygen. So you'll see like silicon atoms attached to 4 oxygens, but then the oxygen has 2 lone pairs. So it can form another bond to another silicon like that, which can form to 2 other oxygens. But you wind up with this, every oxygen gets 2 silicon. Every silicon has 4 oxygens. So you wind up with an SiO2 as the mole ratio. So this is a ratio of a 1 to 2 for silicon to oxygen. But you have this expanded structure where it's forming this 3-dimensional structure. And typically these SiO2s are going to be things like glass or quartz. Sometimes they call it a silica, which is interesting. And like the different structures, a couple of things you should probably know. They tend to be very strong, although more brittle. They tend to not be soluble in water. They tend to have high melting points. And they tend to be poor conductors of electricity. So really just make sure that you know like the different allotropes of carbon, and the SiO2 are for those covalent network structures. Here's a kind of example question that you might see, similarities and differences in the structures of diamond and graphite. So diamond, because the carbons are sp3 hybridized, each carbon has 4 bonds to other carbons. So it winds up with this 3D structure where all of the layers are attached to each other with covalent bonds, whereas graphite is sp2 hybridized. And so you make these layers of carbon with 3 bonds to other carbons, and that makes them really good electrical conductors. And those layers can like slide off as you go. Each of the layers is attracted by intermolecular forces only. So this is an interesting question. So silicon forming another silicon, that covalent bond there is generally weaker than carbon to carbon. That's because silicon is lower down on the periodic table. Silicon has more energy levels. So the valence electrons in silicon, are further from the opposite nuclei or nucleus. And because it's further away, greater distance means it's a weaker attraction. And that has to do with Coulomb's law. Whereas with carbon, you have fewer energy levels. The valence electrons are closer to the nucleus of the opposite atom, and that forms a stronger attraction and a stronger bond.